Office hours, problem solving.
So just to reiterate the earlier question,
Mhm.
the algorithms, if we have to use an algorithm, we should define the algorithm.
I didn't hear it. If we have to make a.
If we're using an algorithm that doesn't already exist, then we have to define it.
Mm-hmm.
Okay.
Yep. Unless it's like something super obvious, like E sub NFA or whatever, or EQ NFA. That's pretty obviously going to be just transform it into DFA and run an EQ DFA. But
Got it.
but if it's like DFA accepts half of every half the strings of every length, then we haven't shown that. So.
And so for an algorithm, we just like describe a term sheet and
Yeah, in the same manner we've been doing. Yep. Mm-hmm. Cool. Cool beans.
Can you explain the example for number 1 on homework? Like just the one.
With the regex one?
Yeah, like the example that you gave us, how that's supposed to work.
So no, I don't know the example. No, that's fine.
Like I'm just confused because I see like in this first cell, for example, you have one starts with a B and one starts with an A. So I'm confused as to how you could get that to work.
Right. So therefore, there's no assignment that works.
Okay. So that means so like
Exactly one symbol appears in every single cell
yes.
in order for an assignment to work. So here's something that may help. How many possible assignments of variables to cells in the table are there? Is it infinite or is it finite?
No, it's not.
Finite, right?
Yeah.
For each one, how long does it take to check whether it's a valid assignment?
Until you get one error.
Yeah. If it works for every, yeah, it's a finite number of steps. That should help.
take a while. It's fine.
Yeah, it takes a ginormous amount of time, but we don't really care here. Unless I said it, whether it's P or NP complete, but yeah. Yeah, so like for here, the first cell would have to be A because the first row has to start with A in this particular case, but for the one that you're doing, for the problem there, you really don't have to look at the structure of the regexes in order to fill the table.
We just know that only one thing can go
In each cell, yeah. In the extension on the optional problem, I say any arbitrary string can fit in every single cell. Instead of just one character, it could be any string, which is obviously a lot harder because there are potentially infinitely many things that can go in every cell.
So just so if row 2 were to be like, I don't know, DD, for example, then that would not work.
Yeah, there's no possibility.
Okay.
Yeah. Well, in fact, these two rows, the regexes for the rows have only 2 terminals in them, so there's no way to assign them anyway. But you'll actually not be concerned about that. It's a lot easier than you guys are making
so.
it.
It's just
Yeah.
a little bit misunderstood as to what we're looking for.
Just as kind of a little more information on unless anyone else has like a homework specific question. The Super Mario Brothers, like where we watched that proof. How is that and then somehow like applicable to Super Mario Brothers as a whole, or do we just take the mechanics of Super Mario Brothers and show that given those constraints?
Yeah, given those constraints, yeah.
Okay.
So like for different Mario games, the mechanics aren't exactly the same, so you can't apply the same proof.
Well, for Mario, I mean, even for, say, keep it just to Super Mario Brothers, the original.
Yeah.
Did that proof of NP hard then? Does that translate to the entire game? Because the entire game has many different.
Yes, you're correct. It's only the goal of. So the question is, can Mario reach some destination or the the castle or whatever. The goal of the whole game is a whole bunch of levels, so it's not the same question.
Okay.
But the question of can you reach a given destination in a single level, that is NP hard.
Okay, because essentially because for different obstacles, you just kind of tweak your rules
Yeah.
to make it so that they work instead of
Yeah.
painting a star, you have a pipe. Okay, cool.
Yeah, the idea is just to make gadgets of whatever the original thing you're working with is. Like with the satisfiability formula, you have one for each variable and one for each clause, and then connect them up.
But if each level is a polynomial time, would the whole thing be polynomial time?
It's polynomial on a non-deterministic machine.
Oh, because we can go in any order.
Actually, no, it's not here. Because it's not guaranteed that that there is a path that takes only polynomial time in general.
Oh, because
Because it can
just
go back.
and forth.
Yeah. Yeah, so it really depends on the problem. A later paper they published, depending on some conditions of like whether objects vanish after the screen goes away, those end up what is called p-space completeness, which is supposedly harder than NP. But if they stay there, I believe it becomes NP complete, or something like that. Yeah.
But so if you were to specify, say Mario can't go backwards, then you could say that you could transfer it to the whole. Yeah, I thought so. I didn't think you could go back. I know the game was
Yeah. So yeah, that seems a good. Well, yeah. So it really depends on how you present it. If you present the problem as you see a constant size window because of like on TVs or whatever, they have constant width and height, that is actually polynomially solvable because you can just look at all four cardinal directions and see what are the possible things that I could reach next, and then just build a configuration graph. And then you just see, is there a way to get to the end?
I feel like it.
But the way that this is presented is the entire level's on the screen at the same time.
Okay.
Which is like Donkey Kong, right?
Yeah.
So.
Yeah. Yeah, so it really depends on how you present the problem.
Huh.
Yeah, this whole area is really cool.
Yeah.
I love the whole area. I'll leave a link to the class that Eric Deming taught about this. It's pretty cool.
And so that will explain why endless world games are not NPR, because they're not. They could go on forever in either direction, technically.
Here we're working with decision problems of whether the answer is yes or no to a particular question. So it really depends on how you present it. Or maybe like a Conway's Game of Life, does it ever go past this particular box? And then, and that is exponentially solvable because there are only exponentially many things in a given grid. But again, it really depends on how you present it. Yeah.
That's not adding any additional input to.
Yeah. So it depends on the number of players in the game because there could be some back and forth, which could add to the complexity. So.
Question about 3.
Oh, which one?
The powering it up,
Mm-hmm.
power it off.
Mhm.
It's approaching it with multiple tapes.
Yeah, that's fine.
Evenly.
Make sure that the number of tapes, if you do a multi-tape solution, is fixed no matter what the input is.
Yeah.
So you can't have it be like the length of the input.
Right.
Like if you use 3 tapes for all inputs, that's fine. Mhm.
I
I'm
don't.
not sure how to.
Well, let's see.
It can't be variable tapes, though, right? So
Yeah, it
that's
can't be.
what I messed up
yeah.
with testing.
Yeah, it can't be variable. So, well, what you're given here is you're given a string, and you have to recognize whether or not it's made up of the same string multiple times from the original language. And we have a recognizer, not a decider per se for the language, right? So I can't just say, oh, if it happens to be like A, B, A, B, A, B, A, B, just run A, B on the recognizer and see if it accepts, right? Because it might run forever. But here's something that might help. How many possible decompositions of the string are there? Only
How-
finitely many. What is a technique that we saw to work with recognizers on possibly multiple inputs?
Right, here.
No.
Got
Yeah.
I do have, I guess I do have a question.
Yeah.
So like, if we talked about earlier in class that, we can use a Turing machine and we know Turing machine is everything mathematically possible, right?
Mhm.
Can we, I mean, if we're talking about a Turing machine that maybe has to process from 1 to some like n, can we say that in an algorithm?
What do you mean process?
Meaning like.
What, like have a counter 1 through n?
Yeah,
Yeah, that's fine.
that's fine, so
Yep.
that's enough. That's
Mhm.
enough. Okay.
Yeah, because a counter can always be incremented. You can always add more to the tape, but you can't add more tapes.
Got it.
So yeah,
Got it.
the tapes are fixed.
The same thing as like 3n.
Yeah. That, of course.
For all that stuff.
Mhm.
That was kind of a question I had, sort of. As far as making a counter on a Turing machine, could you make it? I came up with 2 ways that you could possibly make it. One is just keep adding, 1,
Yeah.
2, 3,
Mhm.
or the other way was keep updating the first cell to be the number that you are at. Do both
Wh-
of those work?
Not the second one
Oh,
because
you could hit it.
yeah, because I have a fixed number of things that it can appear in a cell,
Yeah.
so I can't go arbitrarily high.
But you could make it so like, you have 1, 2, 3, 4, 5, 6. Then when you get to 10, you shift it over, right?
Yeah, that's exactly the same as if you did in binary or even unary, where you just put 1, 1, 1, 1, 1, 1, 1, 1. So, yeah. It's just you're decreasing the number of times you do it. You push over 1.
Is like that Super Mario Brothers proof, is that just well, I mean, just for fun, or does stuff like that,
Add to
is that
society.
analogous to like, how you would tackle a bigger problem? Like, we
Yeah.
decided that we can create a Super Mario Brothers that is NP, so that if we can, like, abstracting from Super Mario Brothers,
Mhm.
like that in itself didn't do much, but like, we can.
Yeah, you can prove NP hardness through these what are called gadget proofs in a variety of ways. So like a problem that I have seen twice in my research is what is called set cover. So what you're given is a set, a base set, and a bunch of subsets of that set. And what you're asked is, can you find k subsets such that their union is the whole set? Like it covers the entire set. And that's NP hard in general. And the way you prove that is you use a gadget proof. So you make a gadget for the variables and the clauses. And then you just make an appropriate set that's only coverable by k things if the original formula is satisfiable. So these gadget proofs are used everywhere. Yeah. So yeah, that problem I've encountered and I hate, but I've encountered that problem twice now, unfortunately. Yeah. I may actually talk about that next Monday when I talk about my research. The idea of I'm making rows of some array and finding what is the best next row to put there. That's essentially the set cover problem, which is NP hard. So the technique now is to find, you can't necessarily find the best row, but can you find a really good row to add to this array to fulfill some requirement? So, yeah. Other questions?
Problem 5, I'm not even trying to get started on that one.
Which one was that?
That's
NFA
minimum.
It's actually not that hard.
Oh, I imagine.
So, can we check in a finite amount of time whether 2 arbitrary NFAs have the same language?
Yes.
Yes. How many NFAs have size smaller than?
Finitely many. So you just check the smaller and see if they're
Yep.
equal. It's much easier than to make.
Yep.
Thank you.
Yeah. So a lot of these problems are just brute force. Just do brute force on everything. So, because don't care about the runtime unless you're talking about the P and NP ones. But the other ones, just brute force everything, unless it's not finite, and then you can't do that. So, other questions? Or we can break early. No more questions?
Wait, that means a question. I was gonna be like, no, wait, that means.
Yeah.
You're like at the end of the.
All right, we'll see you on Wednesday.
My